Good morning. Thank you all for showing up. Wally, it seems like we've just done this before, so welcome back. Thank you all for showing up. I'm always interested in sitting down with Wally because I get more statistics than I've ever gotten out of the entire industry in one place, just sitting here. So Wally, thinking of statistics, the EDA and semiconductor industry seem to be doing really well right now. What's behind it, and do you expect that to continue?
It really is an amazing period. If you look at the semiconductor industry, it's been a 3% growth per year the last 6 years. In fact, actually almost since the turn of the century. And the last couple of years, 2015, 2016, it grew less than 0.5%, and yet 2017, all of a sudden it grows 22%. Wow, that's a big jump, and we're forecasting big growth this year. And of course, all of that passes through. EDA's had a great year, and we can talk more about that. But I think on the semiconductor side, a number of things came together. Of course, memory shortages led to a price increase in memory that was more than 2.5 times what it was 18 months ago. And so while the unit volume for memory did grow, in fact, pricing was an even bigger effect. So memory is about 2/3 of the growth of this last year. But the interesting part, especially for this audience, is the growth that's occurred because of the whole dynamic of what's being designed and what it's being used for. So you have just a wealth of new startups, and they're doing all sorts of new processors for AI, and they're taking off. They're being funded. That's helping the EDA industry. You have the automotive boom for driverless car and electric cars, and all these companies are doing electronic design, but they're also, the automotive industry is buying more semiconductors. And we have just a generally healthy economy for the semiconductor industry, which passes through to EDA.
The nature of the companies themselves seems to be shifting a little bit, though. In the past, we were dealing primarily with chip companies. Now we're dealing with a bit more system companies. Is this just the beginning of what will eventually be chip companies because they'll think that it's not an effective way of doing this and a cost-effective way of doing this, or is it a real shift of what's going on because things are so complicated at a system level?
So I think we're going through one of these waves. We do this about every 20 years. I remember in the 1980s, every computer company started building a wafer fab. And they did it because they could differentiate, or they thought they could differentiate, and then it went back the other way. This time it's a little different. So you take the information technology world, they are very much focused on building both the information collection, processing, optimization of a whole variety of things. And in many cases, they want to design their own chips. They want them to be proprietary. And then you have just the general systems companies who found that they can get differentiation, they can reduce costs by doing chips. So the Apples of the world, for example, those companies have gone from negligible foundry purchases 10 years ago to now they're 13% of the total foundry purchases are going to systems companies. And so they have become designers of and users of semiconductor chips. That's a big transition, while the sales of foundries to fabless semiconductor companies has stayed at a fairly flat 70%.
The number I heard was that for TSMC, on the advanced node, something like 22 or 23% of their capacity was going to Apple.
Well, so TSMC has a unique customer distribution. I'm talking about the total foundry business, but yeah, TSMC has a very big customer who designs their own application processors and fills an entire fab at TSMC.
So are we going through a period where we're going to see consolidation and then disaggregation, or are we going through a period where there's new companies starting up in addition to the consolidation? 3 years ago, we looked at out on DAC, and the big story was the number of companies that's out here is shrinking and the companies are disappearing. Suddenly, they're back.
Yeah, well, the startup fever is the most amazing statistic. So after declining for most of the last 15 years, the number of venture-funded startups in 2017, the amount of money that went into venture-funded fabless semiconductor startups went to $900 million, and in the fourth quarter of 2017, it was almost $500 million of venture-funded startups. And you look at what they were designing, more than half of them were variants of either AI processors or blockchain processors or new kinds of processor architectures. And that stimulates, there will of course be a shakeout over time. You can't have that many companies competing for similar markets, but it's one that probably won't shake out for quite a while because most of these are specialized for particular applications. And I think same thing's true on the other side. I don't see a time when Apple's going to go back to just buying generic application processors or even turning over the design process to ASIC design companies. That looks like a long-term change.
One startup that has gotten a lot of attention, less of a startup and more of an established company when it got acquired, is Mentor. Have you guys fared under Siemens?
It has been wonderful.
Why?
In a word. So first of all, you would think when the announcement was made in November of 2016 that customers would worry, oh, what's going to happen? Is the strategy going to change? But 2016 turned out to be an outstanding record year. But we've just completed 2017 now, all as part of Siemens, and it was an even bigger record, an all-time record, and almost all of our businesses set all-time records. In fact, IC design actually stronger than system design, but they were all at an all-time record. And I think if you go back, when Siemens announced the acquisition, they said, hey, we are doing this to invest, not to cost reduce. And they have been absolutely true to their word. The investment in R&D has caused us to grow our headcount since the announcement in just the IC design R&D in the various groups, anywhere from a 15 to 35% increase in headcount. They have facilitated the organization to continue to function and serve customers. So I think if you talk to customers here, they would say the people they deal with at Mentor are the same they've always dealt with. Our turnover has been very close to our long-term historical rate, but our acquisitions have accelerated. So we've done more acquisitions since we've been part of Siemens than we've done in any year since 2002, and 3 out of 4 were IC design. We just announced Ostemper on Friday, but we had done Seracall before, targeted at 5G. We had done Invalido at targeting towards simulation for IC and machine learning. We did Infolitica, which is more system-oriented modeling. But anyway, it's great to be part of an organization that can afford to do this. Mentor has a long history of losing out on bidding wars in acquisitions. We don't have to do that anymore. And so where we see opportunity, we now have the power to go after it and do meaningful things.
Okay, well, now that you've got a fat checkbook, what does that mean in terms of what you do with your tooling? What do you actually do with these things that you didn't do before? So in the past, EDA pretty much was focused in just on the chip world. We've talked for a long time about extending this out into the system world. Is that happening?
Absolutely. But I should note, we've talked a lot about chips, but Mentor has always had a significant portion of our revenue from system design as well. And that goes back historically to the start of the EDA industry as we know it today. In the early 1980s, the Daisy-Mentor Valid wars were actually more about system companies than they were IC companies. And the system companies made standardization decisions. And this is the big automotive and aerospace kinds of companies that wanted to have a common infrastructure, use common tools, have common libraries. And so those companies, particularly military, aerospace, and or defense and automotive, just made those decisions, and Mentor won most of those battles, and those people have stayed with us till today. So that's always been about a third of our revenue, and that includes all types of system design. It includes wiring and computational fluid dynamics and thermal analysis and printed circuit board and so on. The thing that's new today is that with this boom in the automotive industry and all of its tentacles into designing the electronics into complex systems, all of a sudden there is a need for systems tools in addition to IC design tools, and there's a need for system design tools that in fact can be well integrated to the rest of the system. You can't design the wiring for a car in 2 dimensions. You have to have the data from the mechanical design because it's a 3-dimensional problem. You have to know that the wire bundle will fit through the hole in the door, and it turns out that wiring is an extremely complex place and route problem with thousands of constraints. It all comes from our chip design heritage in a way, but it's unique to systems.
The engine of this is still the semiconductor, and at a time when we probably need more processing power and we're dealing with more data than ever before, Moore's Law, if it's not completely dead, is certainly running out of steam. You're not getting the same kind of performance improvements at each new node, and it starts going down even as you get into 5 nanometers, 3 nanometers, even with nanosheets. We're starting to move into different architectures there, different packaging. How do you see the architectures changing, and also is it time to get away from a von Neumann architecture?
Okay, lots of questions there. One is just Moore's Law, and as Gordon Moore himself has said, Moore's Law is an exponential, and no exponential is forever. We've known that for a long time. We just keep being amazed at how well we continue executing. But Moore's Law is driven by feature sizes and wafer diameters, and that's where most of the cost reduction in the cost per transistor and even the power per transistor and other features has come from historically. Going forward, it's going to be other variables that allow us to continue to go down the curve. But the cost per transistor is on a learning curve. It will be here forever. Obviously, with memory today, with NAND flash, we're growing to 128 layers vertically with minimal reduction in feature sizes, and that reduces the cost per transistor. All of that will continue. We will continue down that learning curve, and it will provide predictions for the future. So it's just that now, more and more, each node will be named as a different node, but they don't actually mean the features will necessarily decrease, below 3 microns or whatever the next one is.
Well, we're certainly moving in multiple dimensions here that we were not in before. Before it was all a planar approach, and we had a roadmap for that. Now that roadmap doesn't seem to be working, so we have to go in different directions.
Absolutely. So that brings in multi-die packaging, and it brings in stacking, and it brings in all sorts of different ways that you can provide more functionality for a lower cost, and that's what our industry is all about, and that will continue long after I'm gone.
But that's just one piece of it too, right? Because now we start looking at things going, okay, if we're looking at the architecture, why don't we look a little bit further? What happens to neuromorphic computing? What happens to potentially some other new architectures that we've never even considered before?
Yeah, and that I think is the exciting part. The von Neumann architecture that's been with us through most of the history of the computer industry is very efficient at computation, but there are things it is not very efficient at, like pattern recognition, for example. And pattern recognition can be graphical imaging, but it's also sound and taste and smell and all those things. Your brain does pattern recognition very, very efficiently. Not very many cycles. You pick up the phone and a friend of yours is calling, you can tell in the first millisecond or so who it is. Computers for speech processing are nowhere near that efficient, and image processing takes up a large share of your brain, you have to think about ways that you can do things differently. So one is doing more per cycle. Another, power efficiency. We are still, depends who you listen to, but somewhere between 6 and 9 orders of magnitude less energy efficient than the human brain for the kinds of computation that the brain does well. And so it means new architectures are going to be accepted. They're going to be designed in. They will have machine learning in many or maybe even most cases, because your brain has the ability to learn from experience. And I've probably visited 20 or more companies doing their own special purpose AI processors of one sort or another, and they each have their little angle, but I think you're going to see them in specific applications increasingly, and they will complement the traditional von Neumann architectures. Neuromorphic computing will become mainstream, and I think it's a big piece of how we take the next step in efficiency of computation, reducing the cost, making it, doing things actually in both mobile and connected environments that today we have to go to a big server farm to solve.
You know, you go back 5 years ago when people were talking about the IoT, which eventually became all edge devices, and most people thought that these were going to be really dumb devices and sensors sitting out on the network. Reality is this is a completely different type of approach than what's happening today. We're getting much more sophisticated, almost one-off type of approaches. How do we deal with that kind of almost a mass customization of a design?
Well, customization is very good for the people here at this show because it means lots and lots of custom designs, lots of custom design tools to both design and verify those designs. And if Makimoto-san used to talk about Makimoto's waves, where we go through waves of standardization and customization, and we do, as you say, seem to be going into another customization wave, and these things last 10 to 15 years, and that's good, and then we find the efficiencies of standardization take over. But the EDA industry, this is their core business. It's not a case of developing new capabilities so you can do this. It's basically what we do, and it's going to grow the customer base. And it's amazing to me, every year the number of design starts increases. And despite everything you hear about, wow, only really big companies can afford to do IC design today because it's become so expensive, you know, not true. Not all designs are done at 7 nanometers. There are designs being done throughout the range of nodes, and also there are ways people are getting money together to do the 7 nanometer designs. So I think for your question of how are we going to handle it, hey, bring it on. The industry would love the additional revenue.
Do EDA tools as they exist today, will they solve all the problems, or are there going to be some discontinuities coming up?
Yeah, there's going to be one of our major discontinuities that only occurs every 2 or 3 decades, and that's an abstraction change. So not too many in this audience were there to see this, but I remember when we went from schematic capture to RTL, and you think, I have some others out there who were here. Yes. Anyway, you would think that's not that difficult, but let me tell you, it was difficult. And so the new college graduates and the less experienced engineers, I mean, they jumped onto Verilog and VHDL just overnight and started doing their designs. And the people who in their 30s, say 10 to 15 years experience, they got it. They didn't get it as quickly. But the old experienced engineers, and by old I mean over 40 or thereabouts, a large share of them never made the transition. They continued to do their designs with schematic capture. Eventually they maintained what designs we had left that had been done with schematic capture, but they just didn't make the transition. Well, so we've been a long time with that level of abstraction. Basically, everything is done today at RTL, and as complexity increases, you have to change abstraction. We will go to high-level synthesis. We will go to developing certainly the data paths, and all these AI algorithms will be implemented in designs using high-level design. And I think we've said this, gee, this is inevitable. Actually, there have been products in the market since 1993, but what's happened now is the whole infrastructure is there. You can do the design, the verification, everything at the level of C, for example, C++. And so now the world has made available the capability. Now the question, who's going to go to it? And it's appearing to be just like the last one. It's the new college graduates. It's the Googles and Facebooks and Amazons. If you go there, you find these people have already adopted it. They're writing the core functionality for data processing is being written in C and synthesized and verified at a high level. They're looking at alternatives. They analyze power dissipation. They do trade-offs of power, performance, and area, all at the next level of abstraction. And the same will happen just as it did with RTL. But you'll want to mix. You'll want to use the appropriate abstraction for what you're doing. So I think control logic will tend to stay the majority where it is. But RTL designers are finding that by starting with C, that they can do a large share of the design, trade-off analysis, and so on early. And so this will be the next abstraction wave.
What's taken so long in hardware? You think about what happened in software where they've gone to abstractions like Hadoop and Python, and they've done a pretty good job of really raising the abstraction level and making it very simple for people to do this kind of stuff. Is hardware just that much more complicated, or
Well, there are two things. One is the whole infrastructure has to move, and for design, the infrastructure is large. We have IP, we have libraries, and we have experience. And the experience building starts all over. Now, in the examples you're talking about, somebody can go do a project and use a different computer language and write software a lot more simply than you can go and get a whole design team to move its whole infrastructure, retrain its people, and move its experience base. And the other part is really nobody likes change because they've got so much they've got to do. They're busy enough without all of a sudden learning a whole new methodology and moving on. So the word in EDA has always been, if I can just do one more design with the old methodology, I'll do it. And you eventually get to a point where the complexity grows or the power challenges become so great, you have to make a change, and you make the change. It's just that abstraction changes are more difficult than just adding power analysis to your flow or analyzing for electromigration or things like that.
You brought up AI and machine learning. Those are two of the hottest buzzwords I know about in the market right now, particularly for chips that people are designing. How about for using those tools for designing the chips in the first place? Is that happening? So in EDA, do you see a broader application of this?
Of which?
Both AI and machine learning.
Oh, yeah. So there are dozens, maybe hundreds of projects around the industry that use machine learning to improve performance of their EDA tools. We have them all over the company. We've done a lot of advertising, for example, with Solido. Solido is able to use machine learning to figure out where you get 90% of the or 99% of the information from a dramatically smaller set of simulations, so you don't end up having to do hundreds of thousands or millions of simulations to characterize a particular library or piece of IP. And so the savings comes from the algorithms improving themselves. We've got Caliber's got all sorts of programs, I haven't even kept count, where they are looking at looking at large databases over time, and for example, doing resolution enhancement. They'll look at the entire rule set is applied to a design, and then look for what is an optimum way to then develop the actual code that will set the resolution enhancement to achieve the desired objective and so on. Lots of those, and they're at all the EDA companies, really.
One of the things about AI and machine learning, though, is once you do the training algorithm and you put this out into the marketplace, you're not quite sure exactly how this is going to behave. So instead of getting a very fixed answer, you're getting a distribution. And when you're dealing with a nanometer or two, is that good enough?
Well, if it's better than what you're doing today, of course, it's good enough. I think you're also suggesting the issues of, wait a minute, if I verified this product and I sell it and it changes its behavior, it's no longer verified. What do we do about that? And what does a car manufacturer do? And those problems, I think, have to be addressed. And they are being addressed. We introduced a product called Tessen Mission Mode that lets you design into your integrated circuit the ability to dynamically test any subsystem that is JTAG compatible, so that the car manufacturer can build in software so that when your chip is not doing anything, it's self-testing itself against a set of criteria that the system manufacturer has established, so that it can, in fact, have a dynamic lifetime of self-test. And I think you'll see the same thing evolving over time as you get more and more neural networks and applying machine learning to chips, to boards, to systems. Then you'll get more and more ways to verify that they haven't modified themselves into a space that could be dangerous or non-functional, that kind of thing.
One of the big applications of AI these days is in autonomous vehicles, and there seems to be a big rush on here to get these cars out the door. But for most people that I talk to, and probably most people that you talk to, we go, is this really going to work at the level that we think it's supposed to? Are these systems designed well enough, and are we far enough along in this? Are we at the level where you would trust one of these systems with your family driving down the road?
Well, so we've seen a lot of autonomous driving-like features make their way into cars, but full level 5, that means no steering wheel, all that, I think is a ways off. We see all these announcements of companies that are going to call something level 4, level 4/5, and so on, but they are steps along the way. I think at Mentor, we actually took a little different approach. We've always done embedded software for infotainment, and that's become a very big and successful embedded software business. And we were moving into the area of ADAS, the driver assistance. And we looked at the way infotainment evolved, and it was one module at a time. You did a GPS controller and an audio controller and a backseat video and so on. And by the time you stacked all these together, each one had its own stack of software so the whole system was unmanageable, slow, hard to maintain. And so ultimately, Harman and some others developed integrated infotainment. And we felt that the same thing had to happen with ADAS, but we needed to know what the architecture of the driverless car was going to be, so that when you develop the blocks in ADAS, they fit into this architecture. So we jumped a step ahead. We introduced a driverless car architecture and DRS 360, and basically that set the ground rules and provided emulators to simulate the behavior of multiple sensors and the whole sensor fusion, test the algorithms for sensor fusion, put it together, and ultimately you come to the conclusion that Most of the processing ends up centralized because you have to be able to overlay the LiDAR with the radar, with the visual, and so on. But it also gave us a framework for how to develop the pieces of the ADAS electronics to fit in. And so I think that's an important part. As the whole industry goes to level 4 and level 5, they need a compatibility going forward so that you don't have to have the full level 5 car before you introduce many of the level 5-like features in your level 4 or level 3.
You know, you're talking about this balance between what gets central, what gets goes to the edge. That balance is being changed around in a lot of. That's one of the parameters that we're starting to work with in a lot of the edge devices right now. What does the IoT shape up as because of this? Is there even an IoT, or are we now coming down to lots of vertical markets, each with its own particular use case?
So to me, this is one of the exciting things for all of us here at DAC, because we talk about the cloud, and then we talk about the fog, and now people talk about the mist, and we talk about edge nodes, and now they're talking about end nodes. But the reality is intelligence flows downhill, always has. There were mainframes, and then we put mini computers in between, and then we put PCs in, and then we put intelligent peripherals. Well, the same thing is happening here. The edge nodes are becoming more and more intelligent, as are the end nodes, and it's natural that they should, because in cars, for example, you can't guarantee cloud connectivity, so the car has to be able to do a lot of local processing. Those edge nodes have to be intelligent, and gateways and edge nodes, you can't communicate everything to the cloud. They need to do pre-processing of data. They need to consolidate. You can't afford all the bandwidth. You can't afford the cost of the paying for the cloud, and you can't afford the latency associated with just sending it to the cloud and getting the answer back. So the great news for EDA is those chips that were going to be very dumb with very little functionality are going to be smarter, and they're going to involve multiple technologies. They're going to have not just analog and digital, but RF to communicate, and maybe MEMS, maybe photonics. Going to be very challenging system-like designs where you have to simulate multiple technologies together, integrated effectively, do local processing, and ultimately, as you note, do AI processing, do optimization, do everything you can do at the edge or beyond, and save the things for the cloud that have to go to the cloud.
So let me go back to something I was talking about before. So how do we get these chips out on time, these devices out on time, in the market on time for a reasonable price? I think about the electronics that are going into some of the AI systems in these cars, and I, for the life of me, can't figure out how anybody's going to afford them.
You mean afford the actual chips?
For the whole system, an AI system, you're basically putting a supercomputer in a car.
Yeah. Well, first of all, the path is always toward reduced cost. The cost per transistor last year came down 33%. The long-term learning curve is on the same slope it's always been on. And so I think this will continue. And you look at the cost of LiDAR, for example, has fallen from $100,000 plus down to thousands, and will fall to hundreds. And so I think the learning curves are going to be, we know the challenge, and our customers know where the price point is, where they have to put things in. The part you mentioned about the design cost, I think it is incredible that design efficiency, cost per transistor for EDA tools, for example, decreases at the same rate as cost per transistor of chips. So cost per transistor of EDA tools last year decreased approximately 35%, because it has to. Because semiconductor companies spend the same percentage of their revenue on EDA today that they did 25 years ago, and they have to give their customers a price reduction, and it gets pushed back down. So the tools have to handle more and more data and do it in the same or less time. And hey, we've been doing it for a long time.
So
We'll
this is going to
continue
make
doing it.
EDA fat and happy.
fat and happy is questionable. We are always squeezed by the unreasonable demands made by our customers. But the fact is the EDA industry is a growing industry, just as the semiconductor industry is. And we're very generous with our product, but I know our customers want us to be able to hire the best and the brightest. So somewhere there will be a middle ground that allows us to continue to grow and continue to be profitable.
Okay, I can ask questions all day, but would somebody like to ask a question? Yeah, there's a mic over there. Standing. Sorry, Peggy.
Oh, it's Peggy. Oh, okay. Oh, dear. I already anticipate this is going to be a tough one. Yeah. Okay.
That could be tough. So, Wally, you are on the board of the ESD Alliance. And the ESD Alliance, I'm presuming, voted unanimously to join SEMI. And the rumor's out that SEMI would like to fold the show features of a DAC-like show into their global behemoth shows, which are huge. That's ginormous, really, unequivocally. If Synopsys and Cadence pull out of exhibiting here at DAC because they're going to put their emphasis on the SEMI shows, is Mentor going to continue? And if Mentor doesn't, is there a future for DAC after this year?
So I think all of that is under debate. The DAC Executive Committee is considering what the best approach is. The SEMI, we have made clear that ESDA will be part of SEMI, and the major suppliers have said we will exhibit at SEMI. That doesn't mean we won't exhibit at DAC, but we will, in fact, take advantage of SEMI's broader move toward design as well as manufacturing. And I think all those details have to be worked out as to how does this evolve so that we keep our ecosystem together, we keep the design community together. And I think one of the great things we have here at DAC that I'm sure that SEMI would like to preserve is the fact we have academics, we have industry people, we have designers and developers of design tools all in one place at one time. And that's something that we would really like to maintain.
So I'm hearing you say if Synopsys and Cadence pull out of DAC, Mentor will still be here.
I didn't say that.
Okay.
They said, well, I have to see how this evolves. You know,
Okay.
It's still very much a transition in the making, and the parties have to come together and decide what the best approach is.
When will we know the results of that negotiation?
I don't know the
Okay,
answer to that.
thanks.
Okay.
Go ahead.
I guess you can hear me, hopefully. So I guess the question is, per the last question you were answering, like would the EDA is kind of a fat and happy, right? Kind of online with that.
He said that. I didn't say
Yeah,
that.
so the question kind of follow with that. If you look, EDA industry spends about 35% of revenue on R&D, right? And kind of because what you're saying that you have to reduce the cost about 35% per year or something.
Per transistor.
Per transistor,
Right.
to match up with that. So I guess the question is, why can't EDA industry figure out a way to get paid if the R&D expense is so high, which is probably highest in enterprise software, which you can find, which is probably closer to 15 to 20% of revs?
I wish I knew the answer to that. I would say that we do get paid. It's just you're saying, why don't we get paid more given the value we provide? And I think this goes all the way down the food chain. I used to, well, when I was at Texas Instruments, the people in the dynamic RAM business used to say, we sell more technology for $2 than anything in the world. You know, why can't we charge $4? And the answer is because there's someone who will sell it for $2. And also, the applications are enabled based upon the cost. And we've got sort of the same situation. If we went to the semiconductor industry and said, let's change nothing except that you pay twice as much for our tools, someone has to absorb that cost. They would love, well, I don't know if they'd love to, but if they tried to pass that on to their customers, two things would happen. One is applications that are using their products would not be able to use their products at that price. And then the additional effect would be a rebellion from those customers. But I absolutely advocate what you're saying. We do provide far more value than what we're paid for. We try to get paid by differentiation, by doing things that are critical, that save our customers money and get to market faster, that are not generally available from our competitors. And we do. EDA companies, when they get a franchise in a particular product area, we're well rewarded. We make a lot more money in the products where we are the leader than we do in products where we are a follower. And so I think we'll continue trying, but there are some realities of the world that say it probably won't get to the level where we're actually paid for the amount of effect we have on the industry.
Let me do one additional add-on to that, and we only have about time for one more question after this. Does it get easier now that you're not dealing with exactly the same companies? So chip companies, to a large extent, were a middleman in this from the systems companies. The system companies are now taking a lot of this in-house. Does it get easier to get paid more, cutting out the middleman?
Well, you'd think so, because after all, now those companies are one step closer to the end product, and so you've removed this intermediate cost. I think the reality, though, is when a system company like Bosch does a lot of IC design, when they do it in-house, they inherit most of the costs that the semiconductor company would have. So the only arguments around margin stacking, and when you get into the margin stacking, then you have the offset of efficiency of designing a product for many customers, and they're designing it for one customer, so the volume is lower. And so in general, that seems not to have an enormous effect. I'm not expecting system companies to pay dramatically more for their tools than what we sell the same simulator to a chip company for, but I'd certainly encourage people to try to make that happen.
Last question.
Okay, first of all, I wanted to say how happy I was to hear you give the emphasis to the raising of change in abstraction level for doing design. But I think you forgot to mention one of the blockers, besides, people liking to do things the way they've always done and having, the control that they normally have cycle to cycle. But I found that the blocker has always been formal equivalence between the C code, or the C++ code, and the generated RTL. And so how close is Mentor to closing that gap?
Yeah, did we pay you to ask this?
No,
Okay. No,
I do some consulting for you, but you didn't actually pay me to ask that.
I agree. Well, so this all started, 20 years ago when we first started doing it. That's what Calypto's business was. And it evolved, and so now that formal equivalence is there. It works. You can trust it. It handles the corner cases. It is truly has come of age. And so that's one of the things when I talk about the whole infrastructure of changing abstraction. Formal equivalence checking is a piece of that, and it is, in fact, a piece that works and that you can buy today. You sound skeptical. Come, you need to talk to, is Badru here? Hook him up with Badru. So.
Wally, thanks for an interesting conversation. Thank you all for coming.
Thank you.